All right, let's get into something that sounds a bit like science fiction, but is very, very real. We usually think about AI as just, a number crunching machine. But what if data itself has a shape? Today, we're going to explore a really powerful idea, that if we can figure out the true geometry of our data, we can build AI that's not just a little better, but way smarter, smaller, and a whole lot more efficient.
So, to wrap your head around this, let's start with a puzzle. Imagine you have something with tons of branches, like a big, sprawling family tree. Now try to shove that into a flat, square box. What's going to happen? Well, all the outer branches, your distant cousins, are going to get squished together, right? You completely distort their real relationships. This, right here, is the exact problem our standard AI models are dealing with every single day.
And this slide just lays it all out. On the left, you've got flat space. You might remember it as Euclidean space from school. It's the world most AI lives in. And when you feed it hierarchical data, things that branch out, it just runs out of space. Things get crowded, relationships get warped. But on the right, you have curved space, or more specifically, hyperbolic space. This is a totally different beast. It's a kind of geometry that just naturally expands. It gives you more and more room the farther you go, just like a tree.
So let's give this a name because it's a really big deal. We're calling it the flat space problem. And at its core, it's a fundamental mismatch between the actual shape of our data and the rigid, flat world we've been trying to force it into.
The researchers behind this paper just nail it with this quote: "A geometric capacity mismatch." I love that phrase. It's really just a formal way of saying our tools are the wrong shape for the job. Think about it. Hierarchies grow exponentially, right? You have 2 parents, 4 grandparents, 8 great-grandparents, it explodes outwards. A flat piece of paper just can't keep up with that kind of growth.
Which brings us to the hero of our story today. If flat space is the problem, then a different kind of geometry has to be the solution. So let's dive in and get to know this new playing field: hyperbolic space.
So what is hyperbolic space, really? Well, the key idea is something called negative curvature. It's a world where all the geometric rules are used to get a little weird. But the most important thing to understand, the real superpower here, is that this structure means space itself expands exponentially. It's the perfect home, the natural habitat for all that branching data we were trying to cram into that flat box.
Now, I know negative curvature sounds super abstract, so let's try to get a feel for it. Picture the surface of a saddle, or even a Pringles ship. See how it curves up in one direction but down in another? Or think about the frilly edges of a kale or lettuce leaf, how they seem to have way more surface area than the center. That's the vibe. It's a space where 2 lines that start out parallel will actually drift away from each other over time. And that's the whole point. It has all this incredible exponentially growing room.
Okay, so this hyperbolic space is the perfect new home for our data. Awesome. But wait, we've spent years and billions of dollars training these huge AI models in the old flat world. Do we just throw all that work away? Well, no. The researchers came up with a really clever solution, using a method that they frame as a teacher and a student.
Here's the game plan. First, you take one of those massive existing AIs. That's your teacher. It already knows the data inside and out, but it sees the world as flat. Then you build a brand new, much smaller student model, one that's designed from the ground up to live in this curved hyperbolic space. And here's the genius part, step 3. The student's only job is to learn one thing: how to perfectly match the distances between data points that the teacher sees. It's not learning from scratch, it's learning the teacher's wisdom and translating it into its own native curved language.
Now, good science isn't about just building one thing and hoping for the best. These researchers were really systematic. They didn't just build one student model, they built a whole series of them. They started with a really basic version and then kept adding more rules, more constraints to figure out exactly what was needed to make this translation work perfectly.
And this table kind of shows that journey. On the left, you've got the minimal model, which was really just the basic proof of concept. But over on the right, the fully governed model has all the bells and whistles. It's got extra rules to make sure the geometry stays stable, and this is really cool. It can even learn and adapt the curvature of its own space to find the absolute best fit for the data.
So what's the point of all those extra features in the fancy model? It all comes down to this idea of geometric fidelity. See, it's not enough to just dump the data into a curved space. You have to add some guardrails, some rules that force the data to respect its new home. This makes sure the final result is not only super compressed, but also mathematically stable and sound.
Okay, this has all been pretty deep in the weeds of geometry and AI, I know. But let's pull back up. What does this actually mean for the real world?
This is where we go from the how it works to the so what. And believe me, the impact is huge.
First things first, efficiency. And the numbers here are just staggering. The researchers took information that needed 768 dimensions to make sense in flat space, and they compressed it down to just 32 dimensions in their new curved space. That's more than 20 times smaller, and they did it without losing the essential structure of the data. We're talking about much, much smaller and faster AI. And that kind of efficiency could unlock some incredible new things. Just imagine a search engine that actually understands that a poodle is a type of canine, which is a type of mammal, or a Netflix that gets the subtle, branching relationships between movies. We could map out incredibly complex things, like protein interactions or social networks, with way more accuracy. It's all about building an AI that has a more intuitive, geometric understanding of the world.
And all of this leaves us with one last, really mind-bending question. We've seen that hierarchical data just feels right at home in hyperbolic space. But what about everything else? What's the natural shape of music, or the stock market, or even human emotion? It feels like we're on the verge of a whole new frontier for AI, one where it's not about just building bigger models, but about finding the perfect mathematical universe for our data to live in.